Most of it, yeah. Yeah. So welcome everyone to the IISc MSR Theory Seminar Series. Closer. So welcome everyone to the IISc MSR Theory Seminar Series. This week we are delighted to have Professor Mohit Singh from Georgia Institute of Technology as our guest speaker. Mohit did his PhD in Algorithms, Combinatorics and Optimization at CMU, followed by a postdoc at Microsoft Research, New England. He then held various positions at McGill. Not audible? Is it audible now? Yeah. Okay, good. Welcome everyone to the IISc MSR Theory Seminar Series. This week we are delighted to have Professor Mohit Singh from Georgia Institute of Technology as our guest speaker. Mohit did his PhD in Algorithms, Combinatorics and Optimization at CMU, followed by a postdoc at Microsoft Research, New England. He then held various positions at McGill University and Microsoft Research, Redmond. From 2017 onwards, he has been a professor at faculty at Georgia Institute of Technology, where he is also the director of Algorithms and Randomness Center. Mohit has a broad set of research interests spanning areas in discrete optimization, approximation algorithms, and convex optimization. He was also the co-author of the Best Folks 2011 Paper Award. He was the co-winner of the Best Folks 2011 Paper Award for his work on TSP. So Mohit has kindly agreed to give a talk on titled Determinant Maximization, Approximation and Estimation Algorithms. So let's welcome Mohit.
Thank you. Thank you. I hope I'm audible to people at the back. Yes, you can hear me? Or is it... Okay. Yeah. Okay. Good. So let me know if I'm not audible at the back or something. I will. The talk has a lot of material, so feel free to stop me. We will not go over finish all the slides anyway, so it doesn't matter. So if you're not understanding anything, we can go slower. So I'm going to talk about this general model of determinant maximization. It's a very abstract problem. So what I'm going to do is start with a bunch of applications. And I believe some of you might have already worked on those applications, so you might not be able to relate to the problem directly, but certainly the applications I feel that many of people in this room have worked on. And then we'll come back to this general problem and try to understand some algorithms, and interestingly, some algorithms which are just estimation algorithms. I'll explain what those are. Okay, good. So let me start with the outline. Basically, I start with some applications and some results and techniques. I'll focus on two methods of it. One are based on convex relaxations for this problem, and the other which are more combinatorial methods. And then we'll end with some open directions. Okay, so let me start with the first application. Good. The first application is a classic problem in statistics called experimental design. Okay, so what is the problem? So think of you have some unknown d-dimensional vector. You don't know this vector, and you want to know what it is. And the way you can only access it, you can do linear measurements of this vector. So you have a collection of these linear measurements, v1 through vm. What you can do is basically take the inner product of your linear measure, like basically inner product of vi with theta star. And except that every time you do this linear measurements, you also get some Gaussian noise. This noise, let's say, it's some Gaussian with mean 0 and variance sigma square, or like standard deviation sigma. Okay, good. So that's the measurement you can do. And of course, your goal is to figure out what measurements to do. Okay, these are the possible n measurements, but you don't have the budget to do n. Maybe you can just do just a collection of measurements. And maybe you can only do, let's say, k measurements. So you can, out of these n, you can choose any k measurements to do. Now, your goal is to figure out which k measurements to do. Of course, what is your final goal? You really want to measure theta star, and you want to understand which, like certainly don't want to do measurements where VIs are all the same, very similar vectors. Intuitively, you want to pick orthogonal directions, which will give you more and more information, right? So the question is, how do we quantify it? Well, then you will ask yourself is that if I choose suppose I already chosen some measurements to do, let's say denote that by S, by the index of the measurements, then what is my estimate of theta star? Well, of course, your measurements, like estimate of theta star is just the most likelihood estimator. In this case, it's because of a very simple model, linear model, it'll be just a least square. Okay, so you solve this least square problem, you'll find that theta which fits your measurements yi as good as possible, right? Okay, the least square error that you'll do, that you'll optimize. And under these Gaussian assumptions, you can ask, okay, what is theta hat, and what is it? How close is theta hat to theta star? Of course, how close it is should depend on what measurements you did. Okay, so good. And a simple calculation, because least square, you can write a closed form expression, and then you do some simple calculation. You can actually show that theta hat minus theta star will also be distributed like a multivariate Gaussian. Okay, it's a high dimension, d-dimensional vector. It will also be distributed like a Gaussian whose covariance matrix will depend on, this will be like a mean will be 0, but this covariance matrix will depend on exactly the measurements you do. Actually, it will be exactly the sum of these rank 1 matrices, right, for each of the measurements and the inverse of that. Okay? So the way you should think about it is that if your theta hat is this, there is a confidence ellipsoid around it, like this, where the ellipsoids is defined by this covariance matrix. Okay, the bigger this covariance matrix, the bigger your confidence ellipsoid. And I want to make sure that the measurements I do it such that this confidence ellipsoid should be as small as possible. Okay, so question is, how do I measure now? Like if it's an interval, it's nice. Like when 1D random variables, we measure confidence intervals, that's easy. But in ellipsoid, there could be many measures. One measure is to say that I want to minimize the volume of this confidence ellipsoid. Okay? And which is exactly, if the ellipsoid is given by this covariance matrix, minimizing this classically called the d-optimal design problem, is to minimize the volume of this ellipsoid, which is the volume of this ellipsoid is proportional to the determinant of this matrix, right? Because it's an inverse, which is minimizing that determinant is equivalent to maximizing the determinant of exactly the inverse of the, if I remove the inverse. That's exactly the maximum determinant problem. Because we are calculating d-dimensional determinants, I put a 1 over d factor because that's really the right units in some sense. Because d-dimensional determinants will be intuitively exponential in d, right? So I'm just taking the right units by taking a dth root. Okay, so that's really the problem that I'm going to be working at. That's the maximizing determinant problem. Okay, so what is the problem? More formally, like okay, this is, and it's equivalent to minimizing the volume of this ellipsoid. So before I formally define it more formally as well, it turns out that this you could have looked at other objectives as well, and people have looked at, and we'll come back to these at the end of the talk. You would say, okay, maybe I want to minimize the average variance in any direction of this ellipsoid. Okay, that's called A design classically in statistics literature, which is to minimize the trace of this ellipsoid. Or you could say I want to minimize the maximum variance in any direction. In every direction, I should have log. So that's basically minimizing the operator norm or the maximum eigenvalue of this matrix. That's also called the E design in statistics literature and so on. So all of these have been studied classically. There's a huge literature in statistics and machine learning, and more recently on more algorithms as well to design study these problems. So we'll revisit this a bit more when I talk about results, and especially what kind of algorithms people use in practice and so on. But this gives a good segue for me. Yes.
Can you go back one slide? The maximization of the determinant is in a way that we are getting.
So good. So it depends. So exactly. So I intuitively, let's say if you were picking D vectors in D dimension, you would want them to be as orthogonal as possible. In particular, determinant would be 0 if they are not spanning, like their rank is not D for them. But typically, we would the problem is also interesting when you're picking more vectors in the dimension. So clearly, they should span the space, but clearly, and they should be orthogonal. But you're not going to find more than D vectors which are orthogonal in, right? But I'm picking maybe 10 D vectors. So question is, what should I do? It's not so interesting. It's not so easy to think about geometrically. But when the number of vectors you're picking exactly D, then it's a very geometric problem. Intuitively, I will come to that as well. Yes.
If we go from D to 2D, having more dependent vectors actually.
Yes, certainly. Yes. Yeah, there was one.
The word isotropic connection with this.
Correct, exactly. So we'll come to maybe I'll briefly mention, but more or less. Yeah, so more or less you can assume okay, we'll come to that so you can assume that the vectors are in isotropic position in some sense after certain scaling and so on. So those are algorithmically, those techniques are used to put them in isotropic position and use that somehow. Maybe I briefly mentioned it, but I'm not completely sure we'll see exactly. Okay, so let me formally define the problem that we are going to study in this talk. So what is the problem? I'm going to give you a bunch of vectors in RD, and my goal is to approximate this optimal value. subject where I'm also giving you some constraint, combinatorial constraints on which set of vectors can you pick, and what is our objective. If you pick a subset of the vectors, then I want to sum up this rank 1 matrices, summation vi transpose, sum over I in S, and take the dth root of the determinant. And the set of vectors, you can't pick any set of vectors, they should be in your feasible set family, which I'm going to denote by script V. Okay. So for example, script V could be like the one which you're going to study in this is they're going to form a basis of a matroid of rank K. Right. So I'll go, like if you haven't seen matroids, it's not that important. These are the only two matroids which I will really work with. From at least some constraint, which is called a uniform matroid. So that is, I will pick any k vectors. Okay, you can pick any k vectors. So which k vectors to pick over here. The other, which are more interesting, is especially from application point of view, is partition matroids, where I'll say that if all the vectors, I'll partition them, let's say colored red, blue, green, and so on, and I'll tell you to pick 3 red vectors, 4 blue vectors, and 5 green vectors. Okay, and so any such collection is feasible for you, and among all such feasible collection of vectors, pick the one which maximizes this determinant. So this is just some notation which will help us is I'll put all of these vectors which you pick in a matrix, okay, as columns, okay, and that I will denote by like the matrix VS. And you can write this determinant as like this outer product just as in this notation as determinant of VS transpose. Okay, nice thing is that if you're picking exactly D vectors, then determinant of VS transpose is determinant of VS times determinant of VS transpose, yeah. And determinant of VS transpose is same as determinant of VS, so it's just the square of the determinant, okay. And this is something very geometric as well, which will come. I'll show on the next application. Okay. So this is the case of the partition matroid. So basically, these are the only cases you should think about, okay. Like although I talk about general matroids and so on, all the results do work for general matroids, but from a understanding viewpoint, these are the two different matroids to think about: the partition matroid and the cardinality matroid. Yes. Correct. Exactly. Yes. But certainly from a like algorithmic perspective, these problems become very, very complicated. So like yeah, we'll come to those. Okay. So let's look at, because we're talking about this a very convex geometry view as well. So let me tell you a convex geometry problem. Actually, 2 of them which have been classically studied starting with the work of Kachian. As the following. So I give you n vectors in d dimensions, and I want to pick d plus 1 of them. So if I have d plus 1, they form a simplex, right? Like if they are linearly independent, and as such that the volume of the simplex is maximized. Another very closely related geometry problem is if I give you again d, like some n vectors in d dimension, pick d vectors. These d vectors will form a parallelepiped. I want to maximize the volume of that parallelepiped. The first problem actually can be reduced to the second one. I won't do that reduction. It's not very hard to do that. And if I you can write down the formula for the parallelepiped. It's exactly the determinant of VS transpose VS. Okay, the square root of that. So just to last time we had the matrix VS transpose. Okay, so this is VS transpose VS. But other thing for most of the talk, you can just think of the size of S. The number of vectors I'm going to ask you to pick is, let's say, exactly D. Then both of these matrices are both determinant are the same, right? Determinant of. So this is exactly the determinant of VS that we want to maximize. So it can be reduced to determinant maximizations or closely related to it. This has been this problem was introduced by Kachian, where he needed for some geometric algorithms related to ellipsoid, and then he studied more generally, and it has been studied over the years recently as well. So again, this is a special case of the determinant maximization. Exactly because, as I said, this objective is essentially the same when size S is D. Okay, when it is not, then also the same techniques kind of work. All like that. Okay. Next application is just to show you basically if I instantiate these vectors to something special, I can actually capture many different problems. So let me capture a problem from network design. Okay, so one of the problems in network designs is typically mainly what is a network design problems is that I give you a big graph and I want you to subselect some of the edges such that which have some nice connectivity properties. Okay, so for example, and there are many ways to do it. There is a classical problem for survivable network design, but I'm going to do a slightly different problem. So I give you a graph and I want to find some subset of the edges F. I don't want to pick all the edges, but some subset of that, such that the set of edges you pick satisfies some combinatorial constraint. Like for example, you don't want to pick more than k edges. I have a big graph. I want you to pick k edges, but I want them to be well connected. And now the question is, what is your notion of well connectivity? And one of the notion which has been quite studied recently is that you want to maximize the number of spanning trees in the graph. that you pick. So I have a graph, I pick k edges out of it, such that among the subgraphs that you pick now, I want to make sure that there are as many spanning trees as possible. The more the spanning trees in it, the higher the connectivity. It turns out this is a special case of, again, the determinant maximization problem. And the way to do it is you instantiate, like you pick a vector, or you, for every edge, you're picking whether you pick that edge or not. So I will, like for every edge, I'll introduce a vector. Okay, so for, let's say edge is between two vertices A and B. So my vectors will sit in the R to the B. And my vector would be, I'll pick 1A minus 1B, pick any orientation. Like, yeah, so 1A is a characteristic vector which only has one non-zero coordinate for the vertex A. And 1B also has only one non-zero coordinate for the vertex B. Rest of the coordinate for all the vectors are 0. And you can just go, like, define what is known as the Laplacian of this any graph is the sum over the edges of this, the outer product of these vectors. And a very nice formula from Kirchhoff from like close to 200 years ago, 150 years ago, is that the number of spanning trees is very closely related to the determinant of the Laplacian. Actually, I have added this term over here just to make sure, because the Laplacian is not full dimensional, all of these vectors are orthogonal to the all one vector. But that's what really, in some sense, you should really think of them as the determinant of the Laplacian, which is the sum of the outer product, right? Okay, and you're just deciding which edges to pick. So this is also a special case. The details are not that important. Just to get the idea across, the determinant maximization is a very generic model which captures problems not only from statistics and geometry, but also from network design as well. Yes. No, not necessarily, not directly. There are close other notions as well. Like as I said, you instead of determinant, we could have looked at other objectives, like the minimizing, like the trace, or the maximizing the trace of the inverse or the eigenvalues and so on. Some of those are more closely related. Okay, before I tell you results of the determinant maximization, let me tell you one more application.
Is there an exception?
You can make one, I guess, but the question is counting directed spanning trees is, you can do that, but it's not so straightforward. So you have to be very careful. Yeah. So I don't know any results for this problem for the directed version. Okay. So good. Let me tell you one more problem, which I believe some of you would have studied as well, is about allocation of goods. Okay. So this is a problem from a fairness perspective. So I won't spend too much time, but what is the goal over here? I have, let's say, M goods and D agents. So they're D players, like in this case, 2 players and 3 goods. And each agent has a certain utility, how much he values. This agent values, for example, this good as value 2, but that good as value 1. And this agent values this good as value 5 and value 3. And I want to distribute these agents to these these items to these agents. Okay. We are going to assume, let's assume we have additive valuation. What does that mean? If I give you a bundle of goods, what you value that bundle is just sum of the values of the items in that bundle. Okay, so simple additive valuation. And our goal is to find allocation to maximize somewhat the welfare, and while being fair, like fair in some sense as well. So of course, if I just want to make sure items are given in somewhat to maximum welfare, I would just possibly give item to the guy who values it the most. But then the problem is it's unfair. Some people might not get any item. But to make it fair and maximize welfare as well, there is a classic work going back to the work of Nash, who introduced what is known as the Nash social welfare objective, which is to maximize a geometric mean of the agent utilities. And he gave it from a very, very axiomatic view that this is the right notion as well, especially if the items are divisible. We are looking where the items are indivisible. Huh? You have to give the whole item or not. So what we're going to do is we want to find assignment of these items to the players. Every player will evaluate how much their utility they're getting from their bundle. So I have these D utilities, I have D players. So I have D utilities. I'm going to take the geometric mean of them. And that's what my objective is. And in some sense, this interpolates between a total utility and maximizing the minimum utility of any player. Okay? So it's, in some sense, it's more both good in overall welfare as well as fair to some extent. I won't do the reduction, but actually this problem can be modeled as a determinant maximization problem, subject to partition constraints. This is what we have done with joint work with Anari, Oveshiran, and Saberi. in 2017, which basically we utilized to give an E approximation for this problem. Okay, so the reduction is not very difficult, but it uses some partition constraints to do it. That's a standard reduction for how you reduce any allocation problem to a set objective. Of course, people have also attacked this problem. This problem has been studied in the last few years very extensively. Just from an approximation point of view, this started with the work by Cole and Sucklisis, I'm pretty sure I got his pronunciation wrong, who basically, from which I got to know about this problem. Currently, the best approximation is by people over from Hell, Sid, and others, which gave a 1.4 approximation. They use very different techniques, no connections to determinant maximization. They use connections to, all of these papers use connections to market design and a more algorithmic game theory connections. But this is a very, very different view of things, but it still gives good results. And of course, there have been many recent works which generalize these models rather than additive valuation. We have some model evaluations or other valuations, and there have been a lot of work in this very active area of research. Okay, good. So let me, I hope I've convinced you that the problem is somewhat interesting and a very generic, like always abstract model. This captures very problems in very, which have been studied broadly. So just to remind you, what is our problem that we're going to do? Again, like I have a bunch of these vectors in RD, and I want to pick some collection of them which satisfy some combinatorial constraint to maximize the determinant of the sum of the outer product of these vectors. Good. And the two examples on the constraints, which subsets of vectors you want to pick, are the cardinality and the partition matroid. That's what you want to think. Whenever I move to partition matroids, almost all results that work for partition matroid work for all matroids, actually. If that's not, but the cardinality are separate than the partition matroid. Okay, good. So what has been done for this problem? I would basically introduce this in somewhat table just to give you a brief idea of the exact numbers are not going to be that important what approximation is. It's good to understand what kind of techniques have been utilized, and then a lot of techniques have been utilized for this problem. So I've kind of basically divided the problems into more cardinality constraint or a general matroid constraints. And from a basically techniques viewpoint, there are algorithms which are based on convex programming based methods, and there are algorithms which are based on more combinatorial methods. Okay, so that's in some sense how I divide a lot of this work. So for example, from a convex programming based methods, what has been known is one could do randomized rounding based methods. You solve a convex program, you get some fractional variables, and you do some randomized rounding on them, which was introduced by Nikolov, and when we improved it also with John Bogbesi. Beautiful technique which was introduced about more than a decade ago was spectral sparsification, and this problem is very close to spectral sparsification. I won't go into that, but basically that also can be utilized, especially in the case when the number of vectors you're picking is way more than the dimension. So that's a technique that has also been studied quite a lot. The other technique, which is also called volume sampling, which is another beautiful way of sampling a subset of vectors proportional to some of the volume of the parallelepiped spanned by them. That has been also utilized over here. So which gives actually better results than, let's say, spectral sparsification for determinant maximization. The other interesting thing is, for example, these are all for cardinality constraints. What are the combinatorial methods? It turns out actually these were the results which were known like earlier, and we have been improving these, and especially I had worked quite a lot on some of these papers and improved them slowly and slowly. And then I started talking to statisticians exactly, and they told me basically what they do is just local search. They have been solving these problems for practice for ages, and just local search works. And like, of course, the problem with local search is you don't know, like, firstly, like how good the solution is. The nice thing about convex programming solutions is that you have a bound because you solve a convex program and then you round it. The gap between your solution and the convex programming value will give you a guarantee, and at least empirically also you know how good it is. But with the local search, you don't really know. So one of the things that we did actually, it turns out that local search and greedy algorithms perform even way better than some of these like convex programming based methods. The proofs are not very complicated as well. And these algorithms are widely implemented in statistics software like SAS and other softwares. Okay? They are, yeah. And these are also quite light in some sense, right? Solving a convex program is actually quite heavy, okay? And people have tried it, even like people I've talked to some more people who work on more applied work, they've tried to do this. It's especially as the vectors go in higher dimension, things become quite complicated and numerically especially unstable as well. So that's part of the reason people really like local search or simple greedy kind of algorithms. For general matroid constraints, this is where I start things start becoming slightly more heavy, and the convex programming methods actually work quite well, but they only work to give estimation algorithms. Okay? What does that mean? I can estimate the value of the solution. Actually, you can estimate the value of the with respect to just the E approximation, a constant factor approximation, but I don't know I can't return you a good solution, which is somewhat crazy. How would I estimate without actually returning you? It turns out the way one does it is by giving basically what is my estimation is actually just value of the convex program. I'll write a somewhat crazy convex program, and basically we show that the convex program actually has a very good objective without actually returning you a good solution. To do that, there is a lot of theory that has been recently developed on stable polynomials and strongly log concave polynomials, and that's very utilized very crucially over here. This is something I will not cover in this talk. That's a topic of another talk. This we started work with Nikolov and then later on improved considerably by Anali Oveshgaran and Anali Oveshgaran Vincent for more general matroids. This works when the number of vectors you're picking is no more than the dimension. When the number of vectors you're picking is more than dimension, the problem is slightly less understood. Like as well. So apart from all of this machinery, you also need some techniques about sparsity of convex programs. Maybe I'll briefly talk about it depending on how much time I have. Which basically you again get something estimation algorithms which are way better than the approximation algorithm. The approximation algorithms are exponential. Like I don't think so. Those are the right numbers as well. And again, from combinatorial methods, recently that's most of the term. What I'll talk about in this talk is that you can actually get something like D approximation. It's not as good as the estimation, but it's at least better than the exponential approximation algorithms, which are deterministic algorithms, and they are based on matroid intersection-based methods. Yes. Correct. It's just that it's a matter of just units, right? Like because maximizing determinant is the same as maximizing the dth root. Just that when you think of it in an approximation perspective, then all the approximation factors would have an exponent in D. So that's what I wanted to avoid because the right units are just constant in some sense, right? But even then, you get exponential approximations for matroid constraint. Here, I'm taking the dth root. If you don't take the dth root, it will be e to the d square kind of thing. And this will be e to the d, which is the right units, because really you're looking at a volume, d-dimensional volume. Yes. So if you wanted to determine it, this will be a d to the d, this will be e to the d. But if we are just taking the dth root, this is e approximation. So let me see how much time do I have. Okay, so good. So we are exactly more or less on time. So what I want to do for the rest of the talk is introduce you to because there are lots of techniques which have been introduced this problem. I want to touch upon two techniques. One is based on matroid intersection methods, and the other are based on sparsity. Okay? So I will show you sparsity, how sparsity is used for some of these convex. I write a convex program for you and show sparsity for them to give you some idea of what convex programming methods could use somewhat. And then we'll dive a bit more into matroid intersection based methods, which are a bit more heavy. We'll see how much we get into those. Okay. Yes.
So just trying to compare these three techniques and like a So A is greater than d by epsilon square 1 plus epsilon approximation. A is equal to K order d by epsilon 1 plus epsilon. So is there like how do you compare these?
So basically, like you want to get 1 plus epsilon approximation. You want to make sure how quickly you start getting it. So the smaller the k, the better it is. So in some sense, this result is the best one, right? So this would be slightly worse than this, and this would be somewhat more worse than this one. So because you want to, let's say, if you fix epsilon, let's say 0.01, you want to get a 1.01 approximation. How big k can how big k need to be? So this will say you want the k to be 100d. This would say some 300d or something, because the constant. This will say you have to be like 10,000 times d.
So A is very small, like you can do a first kind of a thing.
No, that will be exponential in d. The running time you want to be like okay. So then you can get an e approximation. So
Smaller d, we can get it.
Yeah, exactly. Basically, you can, for example, even for k equal to d, which is really when the problem becomes kind of the hardest. You want to pick exactly d vectors in d dimensions. That's So there are hardnesses are known that you can't get a 1 plus epsilon, you can't get a p-task. So it is APX hard. So you need to lose a constant. It's not E, but some other constant, like bigger than 1. Yes.
Understand the difference between these two. So if you constrain k vectors that do not form a basis, will the determinant not be 0?
So there are two bases of what? So there are two things. One is your constrained matroid, and the other you're thinking of as vectors, right? Bases in the linear space. Right. So in this problem, I'm giving you additional matroids. For example, the partition matroid, yeah. But if they don't form a base, like if they don't contain a basis, rather, because right, I'm taking more vectors in the dimension. Yes. So that you need to do. Okay. Yes.
What kind of hardness is also like? Do we know that
you can't get a constant? 1 plus epsilon. There is some constant such that you can't get that constant. That's the only.
It has to be like exponential. Estimation for volume.
Correct. Yes. So there, if you want to do the volume or there's a determinant, there is a constant c that you cannot get better than 1 plus c to the d approximation. Some constant c strictly greater than 0.
And these work for estimation also.
Correct. Exactly. Yes. So yeah, from a hardness, almost all hardness results will work for both estimation and approximation. Just from an algorithmic viewpoint, in that sense, it's slightly, yeah. So actually, I would say this is very similar to why you're doing this. I didn't want to go into this so much, but like it's very closely related to permanent estimation of computation and estimation of permanent versus determinant. That's the kind of thing that is very closely related to where this is. We can talk offline if people are interested, but yeah, but it's somewhat digress from the remainder of the talk. Okay, so let me briefly give you. So I'll give you a couple of slides just to how sparsity can be used. Okay, so it won't be sparsity for this kind of a thing. I'll do sparsity, but for the cardinality constraint. Okay, where it's much easier, but just to get the idea across. Okay. So what I'm going to do is we look at basically the cardinality constraint. I'll write a convex program for you and basically ensure that it is the solution to that is actually sparse. So what does that mean? So let's write a convex program. So I want to maximize this determinant and I want to pick k vectors. So each vector is between 0 and 1 and summation of the xi will tell me is an indicator variable. Whether I pick a vector or not, I want to set it to 0 or 1. Right? 1 if I pick that vector, 0 if I don't. So this is a natural program, and then x I want it to be binary. I'll relax it to between 0 and 1. It turns out this function, the dth root of the determinant, is actually a concave function of the function. If I think of it as a function of x, this is a concave function. I'm maximizing it subject to linear constraints, so you can just solve this efficiently in polynomial time. This relaxation, right? I'm relaxing it because I'm not insisting x to be binary. I'm allowing you to take fraction value. A folklore result. This is a classic result noticed by a bunch of statisticians. This is a book on Pedro. Even he in his book in 1970 called it folklore, so he really didn't know who to give it credit it for. That there is an optimal solution with the number of fraction variables. Like you want to pick k vectors. Think of k now bigger than d, right? Significantly bigger than d. He's saying is the fraction solution itself will set almost all the variables to either 0 or 1. Very few variables will be set to a fraction value, no more than d squared. Some d square values will be fractional. The rest of them will be already all integer. And intuitively now it should be easy, right? You almost all the convex program, you solve it. It already solves you most of the problem. There are few values which are set to fraction, otherwise they're set to 0, 1. Yes.
So can you compute such a solution?
Yes. So the fraction solution, yes, you can send me. I will compute it for you. Okay, in the next slide. Which is a sparse one, you mean? Yes. There exists one, and then you can do this. Okay. So this is only for cardinality constraint. For matroid constraint, you need this convex program doesn't work. You have to write a stronger convex program, but similar kind of sparsity results can be proven. That's what we did in the work, but that's not what I'm going to do. But just to give you a taste of the technique, how would we prove this? It's a simple actually exercise. So what you do? So I will prove this theorem to you just in one slide. So we solve this convex program. Let's solve this convex program. Let's call the optimal solution to be x star. Okay, so that's a solution you give me. It maybe not, it's off, maybe it's not. Now I'm going to construct you a different solution which has the same objective but is sparser. It's so sparse. The way I'm going to do it is x star is what you did. Now I'm going to search for a new solution x. So I want it to be feasible, so I'll add feasibility constraint. I want the objective to be the same. But rather than placing the objective to be the same, I'll place a stronger constraint. I'll make sure that the matrix in the objective that you're putting in, that whole matrix is the same. And I'll come to that. Why are we putting it? So this is a d by d matrix, right? I'm just summing up, right? So summing this matrix. So this is a variable, right? Xi is a variable, xi star is given. So this is a fixed matrix. I'll say the matrix you will get if you pick solution X should be the same one as you would have got as if you pick matrix X star. So first thing is this LP is feasible. Why is this LP feasible? So like this is a minimization. So it's a feasibility LP. Right? I just say find me. Why is this feasible? X star is clearly a feasible solution, right? So, but now I say let's look at any basic feasible solution to this, right? So like any basic or extreme point solution of the polytope introduced by this, that most of the most of the constraints will be defined by these constraints. So how many constraints do I have? These constraints are like this is a symmetric matrix, so they're only d times d plus 1 by 2 constraints really. Or like if you don't want to bother too much, there's no more than d square constraint, 1 per entry. And there's one constraint, this one, so I get d choose 2, d plus 1 choose 2 plus 1 constraint. The rest of the constraints are defined by just the bound constraints. So, and I know like just the basic properties about the extreme point solutions of or basic feasible solution of LP that all the constraints must be the number of variables which are not in the bound constraint can be at most the number of the other constraint that I have. So almost all the variables will be at the bound constraint except for d times d plus 1 by 2. Okay? So good. That just finishes off. That any basic solution will have support no more than k times k. I can get at most k variables to be set to 1 because I'm picking k of them, and the rest of the variables, fraction variables, can be no more than this much. So you wanted to pick k. The convex program is actually already telling you don't have to search over all n vectors. I'll set all of them, most of them to be 0. You only have to search over k plus d plus 1 choose 2. This already actually very nicely was noticed by Alan Zhu et al. Already implies a 1 plus epsilon approximation if k is bigger than d squared over epsilon. The way to do it is you a priori reduce k from k to k minus d square and then give it solve that. And reducing this doesn't reduce by objective by no more than 1 plus epsilon. And then you basically, even after you add it, the whole support will not be more than k. So which we like later on improved using local search. Right? So that's one of the first techniques. Yeah. Yes. Correct. Yes. Correct. Exactly. By just solving a system like a linear program, not a linear equations, but linear inequalities. Basic feasible solution to this LP. Actually, it is conjectured, and that because here I really wanted to keep the determinant the same, right? I really want to find x star, another solution x, which is sparse, such that the determinant remains the same. Here I'm pursuing a higher constraint, like that the whole matrix remains the same. So actually, it's conjectured, and people have noticed in a lot of experiments, maybe the support you need is only k plus d, order d, not just k plus d square. Right? So that is still open, and we don't know how to get. Okay, but this kind of gives you an idea of the kind of techniques that are used for some of these problems, like a sparsity of the convex program, which is really useful. Good. So the second thing that I want to do now is talk about combinatorial methods as well, so which are based on. So again, this time I will move to more like constraints are partition constraints. Okay, just to understand. So again, just to set up the problem, I'm giving you a bunch of vectors. I want to maximize this determinant. And the set of now solutions I'll pick is, think of the partition MATROID, the simple case. I partition my vectors into k parts, and I have to pick one vector from each of them. And for simplicity, for the rest of the talk, let's assume the number of vectors you're picking is exactly d. So I have partitioned my vectors into d parts, and from each part I have to pick exactly one vector. Nice thing about that is because if they are d vectors, this matrix like this will be exactly d of such vectors over here. This is a d-dimensional determinant. So like this matrix Vs will be a d by d matrix. The determinant of Vs transpose is just determinant of Vs times determinant of Vs transpose, because d by d. So I can just do that. Determinant of these two things are the same, which is determinant of Vs squared. And this exactly determinant of Vs is exactly the volume of the parallelepiped spanned by them, these vectors. So that's exactly this square is just the volume of the square. This is notation I will use as we go along. Okay, so equivalently, given these vectors, I want to maximize the volume of the parallelepiped spanned by the vectors, such that I have to pick one vector from each part. Okay? So that's really the challenge. Good. And this is a question I guess was raised earlier. How do I even know that the answer is 0 or non-zero? Right? So finally, I'm saying I'm going to approximate. right? If the answer is 0, I need to return 0 because any multiplicative approximation, 0 times anything, right? The factor d e to the d, I don't care, will return me a 0. So I want to figure out when is the answer 0. Okay. So let's just think about the case first. Instead of the constraint, when we have these partition constraint, if I had a cardinality constraint, when can I pick d vectors such that the volume of the parallelepiped spanned by those d vectors is non-zero? So when is that true? They better be linearly independent, right? I'm picking, they should span the space and they're only picking d vectors, so they should form a basis of Rd, right? That's exactly if and only if, right? That's when the volume is 0. Okay. So good, that's when the objective will be non-zero. Now I'm saying that you can't pick any d vectors, right? There might be d vectors which form a basis, but they might be all in the same part. You can only pick one of those vectors. Now you want to find the basis of Rd such that you pick one vector from each part. How do I solve that problem? Is that problem polytime solvable? Yeah, okay, and this is something many of you might not have seen, or some of you might have seen if you've done a course on computational optimization. This problem is polytime solvable using MATROID intersection. Okay, so I'll introduce you MATROID intersection, and if there's one thing you want to learn from this talk, is MATROID intersection and simple algorithm for that. Okay, and then we build on that algorithm. That'll be more complicated and challenging. I'll try to address, like, basically get across some of the challenges we need to get across this. Like, yeah, just a feasibility problem. How to solve, which is MATROID intersection, and then I want to basically not just find any one, I want to find the one which has the maximum volume, right? The 0 versus non-zero. I'll try to make sure we get the algorithm completely. Okay, good. So this is classic work. So MATROID intersection. So basically, objective of the max determinant problem is non-zero if the feasible set of vectors they form like a basis. That's what we just discussed. So what is a MATROID? So MATROID is like it's formally defined it to be a ground set V. I'll give a ground set V and a collection of subsets of V, okay, which satisfy two axioms. The first axiom is that it's downward closed. So if I have a set which is like these sets in I are called independent sets, and there's a reason they're called independent sets. We'll see. If A is an independent set, if I take a subset of it, that's also independent. So that must be axiom. That must be a property satisfied by your collection of independent sets. The second property is a more interesting one. If I give you two sets of independent sets, so two sets in A and B, one is larger than the other, then I should be able to find an element in the larger set that I can put in the smaller set such that it remains independent. So one nice thing about this is that all the maximal sets in I with maximal independent sets must have the same cardinality, right? Because if one is larger, then I can always make it bigger and bigger, right? Maximal by containment. And those maximal sets are called bases. Okay, again, like a nomenclature we are borrowing from linear independence and so on, and there is a reason we do this. Okay, good. So the size of maximal, these are called bases, and there are two matroids I will introduce which we need. One matroid, so like for our particular case, for us B would be the set of all vectors, and the first matroid I'll define it is where my independent sets would be where you pick at most one vector from each part. Okay. So if a set for you would be independent, a set of collection of vectors will be independent if you pick at most one vector from each part. And it's easy to check that the first constraint is satisfied, right? If I pick in the collection, if I pick at most one, and from a smaller subset, I'll also pick at most one. Second one is more interesting to think. It's saying basically, yeah, if I have two sets where I'm picking at most one from each of them, like each part, and one has more, then I can switch one. Well, you're picking one from each part, at most one, right? If A has more guys, it must have picked the vector from one of the parts from which B hasn't picked a vector, right? So I can use that vector move around. So it's a simple check. You should check it. Yes?
V is partition into PI.
V is partition into PI. Correct. Yes. So there are only D of them right now, right? D is a dimension. Now you have to pick one. Yeah, good. So although you can define the problem where you have infinite matroids, we're working with finite matroids. Everything is finite. There is a theory of infinite matroids, which is also very well advanced, but that's not the way what we go. The other matroid where you will also now see why the nomenclature comes in is linear independent matroid, where my set of vectors are the same, that are vectors I give you. My independent sets are exactly those sets which are linearly independent. Okay, and now you can check those vectors actually satisfy these to both axioms. Okay, it's not very hard to check. Right? If a set of vectors is linearly independent, I drop a few, they'll remaining one will remain linearly independent. If I have two sets of vectors which are linearly independent, one is bigger than the other, then from the bigger one I can transfer one to the smaller one while remaining linearly independent. Yeah, why? right? The span of these vectors is going to be larger. They are linear independent. They have a larger span, right? So there must be one vector which is not in the span of these vectors. If I'll add it, right? Okay, but yes, you have to say.
I was just asking the third example is the set of independent nodes?
No, that is not. No. For a graph, the most natural matroid is actually look at the set of like your base set is a set of edges, and a set is independent if it defines a forest. It says acyclic. Those form the most canonical example for a matroid. Okay, and what I'm saying is the objective of the max determinant problem is non-zero if there is a common basis of these two matroids. Where I'm saying among the vectors, I can find a basis which are linear in your normal vector sense. It's a basis, and it's also a basis of your partition matroid where you pick exactly one vector from each part. Right. So I can find the objective of the max determinant problem is non-zero if and only if there is a common basis of these two matroids. And of course, yes. No, B is given now. Vectors, I give you a bunch of vectors, and now I just say pick any set is in I2 if they are linearly independent. Yes, there was. No, that's not a matroid. So that's matroid intersection problem. That's what we are doing. Right? We are intersecting two matroids. They are not. Yeah. And there's a classic theorem by Helmholtz which says that you can find the common basis of two matroids in polynomial time. Good. So. More, okay, good. And I'll define, basically solve you a slightly more general problem. In some sense, maybe that's something I will not solve this problem for you. This is also not very hard. What we are interested in is some weighted version of this problem, right? Because we are trying to find weighted version, right? But what is our weight? If I pick a set, is the determinant of that, right? Okay, good. Classically, what has been studied is a weight function where our weight is given by this. Classically, what has been studied where the weight function is additive. Okay, so I'm going to explain this to you. And then we'll come back to our problem. Okay. Yes?
Yeah. That includes the outcome, the possibility that such a common basis does
not exist. Correct.
That
yes.
also can be common for algebra.
Correct. Either it'll tell you there is no common basis, or it'll tell you, yes, this is a common basis. But actually, all of these algorithms, another special case of like two matroids, if you think of two partition matroids, a special case is bipartite matching. So if a graph has a bipartite matching or not, that's another can be reduced to matroid intersection of two matroids as well. And all the algorithm matroid intersection actually kind of generalize that in algorithms for basically like finding a matching in a bipartite graph. Okay? So of course, typically either you've done those algorithms or you've reduced it to flows. Flows match flow in a graph can also do this. That's another generalization. That's not captured by matroid, but there are more general structures to do that. Okay, good. So what is studied for weighted functions? Maybe this is what I'll introduce to you and then tell you quickly how we change this algorithm. So what is the problem now? I give you weight for each vector, okay? And rather than our weight of a subset, rather than being the determinant, is just the additive function. I sum up the weights, okay? This problem can be polynomial time solvable, okay? And what is the algorithm for this? So given two matroids, you can find the common basis of maximum weight. Okay? Yes, yes, there's been a lot of literature on yes. And there is also theorem by Helmholtz that the maximum weight common basis problem is solvable in polynomial time. Good. And this generalizes, as I said, maximum matching in bipartite time. Good. So the most important concept in this matroid intersection algorithms is the concept of exchange graph. Okay, so we like define this exchange graph. What is it? So so because I'm solving the weighted version, so I will actually assume I solve the unweighted version. That I will assume there is a common basis. Okay, so I kind of cheating a bit. I'm not telling you how to find a common basis, but if I give you one common basis, how to find the maximum weight common basis. So I've already given you a common basis, and given this common basis, we're going to construct a directed bipartite graph. Where one bipartition will be all the elements of the vector, or think of in our case, the vectors in the set which you have picked on one side, the rest of the vectors on the other side. And I'm going to add an arc from y to x, like think of this as a backward arc. Okay, good. So from y to x, which are the blue arc, if I replace this y by x and I remain independent in the first matroid. Okay? And for the second, and I'll add the edge from forward edge arc, which is my red arc, if I remove y and add x and I remain independent in the second matroid. So that's how I add this, make this, this is called the exchange graph. It's very closely related to also when one you do for augmenting paths and bipartite matching as well. And now I put length on the vertices. What is the length? Length I put to be the weight if for all these guys, and on the elements which you did not pick, I'll put the length to be the minus of the weight. And the theorem is that S is a maximum weight basis, right? S is your current basis, and the S is a maximum weight basis if and only if there is no negative length cycle in this graph that bipartite graph. And once you do this theorem, it's not very hard to check this, but given this, the algorithm is simple. You start with any common basis, and then you find this exchange graph for that basis. And if there is no negative length cycle, you declare you have the optimal maximum weight. If there is a negative length cycle, it's important you find the one which has the shortest hops, the shortest number of edges in it. Okay? And then you say, I have a cycle, it will pick some t vertices on this side, t vertices on this side. You replace all t of them by all t on the other side. Okay? So that's your new set, and then you recurse. That will have strictly more weight. Intuitively, that should be clear. It should have more weight, right? Because how much your weight will increase, you will, if from a cycle, you will remove the length of these and add the weight of these guys, right? And that this negative part is more than the positive part, right? So I'll get more weight. My weight will clearly increase if I do this. The challenge is to show that now this set is independent in both matroids simultaneously. I've removed a bunch of elements and so on. So that requires the important case that it's the shortest of negative length cycle. So that's the algorithm for maximum weight basis of this. And the only thing is, how do I find this? How do I find negative length cycles in okay, right? This is the algorithm you should have done in the algorithms course as well, at least all the students, right? Okay, yeah. Okay, yeah, you have to be careful, but yes, you can apply basically, right? You can either find shortest path algorithm, right? Either they'll return your negative length cycle or we'll find your shortest path, right? The only thing is I want a shortest hop negative length cycle, so one has to be a bit careful. The shortest hop one, but you can do that. Okay, so what is our challenge? First challenge, okay, before we go forward, maybe let's just understand how this exchange graph is for our special cases of two matroids. Our matroids are somewhat special, right? The first matroid for us was the partition matroid, right? So partition matroid, right, which are the backward edges. So I'll add an edge between a vector v1, which I picked, and another vector on the other side. If I exchange them, they remain independent. When they remain independent, these two vectors should be better be in the same path because I'm not allowed to pick vectors more than one vector from each path. So this vector will have a back edge to all the vectors for the from whichever part it's coming from for all those vectors. Okay? So that's quite easy to understand. Now, question is, what are the red edges? Red edges are linearly independent, right? What it's saying is, I will add an edge from this vector to this vector. If I move this vector, add this vector, and then it still remains a basis, right? This is a basis in the linear independent sense. Good. When is that true? Actually, this is a nice characterization of it. What you'd say is, I want to understand, is there a red edge between this guy and this guy, right? How do I do this? This vector, this is the basis of RD, right? This is the current basis. So this vector can be written as a linear combination of these vectors. So let's just write it for any vector u. Let's write it as a linear combination of the vectors I've chosen. This is a basis. So this will be some real numbers, right? The coefficients of that AUV times B. You will have an edge, red edge, as long as AUV is non-zero. Okay, that's basically the claim. It's very complicated, but once I tell you, it should not be hard to check. Okay, that's exactly when I add it and remove it. If AU is non-zero, then you will remain linearly. And now, one thing the challenge for us is our weight is not additive. Okay? Our weight was like our objective is actually a determinant function, which is not an additive function, right? I give you more vectors. It's actually a log sum modular function. It's log sum modular in some sense. So it's more complicated. So one way to get around this is what we're going to do is put weight on the edges rather than the vertices. Okay? So this is not too complicated. But what we're going to do is, firstly, the weight on the blue edges I won't care, but only on the red edges I'll put. And what is the weight on the red edges I'll put is basically the volume, change in the volume if I replace this vector by that vector. So how much ever my volume, new volume is divided by the whole volume. Because I'm like that, that's what I will put it. Okay. And the backward edges will get a weight of 1. I really don't care how, like for me, that's not very important. Question is, what is this crazy amount? Okay, and a beautiful, nice fact is that this is actually exactly equivalent to that coefficient. I don't have time, but the proof is just again one line. This is exactly the absolute value of the same coefficient. You write u in the basis of S, and you look at what is the coefficient of v in that basis, because if you want to put this edge from u to v, what is exactly the coefficient, the absolute value of that, that's exactly this ratio. So, you can think of it as also as Cramer's rule, yes. But the argument is even much simpler, right? Like Cramer's rule will give you a lot of other things, right? Yeah. So you can certainly apply that. That's a big hammer, but yes. When should I stop? Can I go? Can I go for 5 minutes? Okay. Good. So one thing what we want to do is mimic essentially what we did earlier, except I'm not placing negative weights, so one has to be slightly careful. What we're going to do is basically I'll find a cycle in this graph where now my weight of the cycle, I'll think of it as a product of the weights on the edges. I'll claim that as long as my solution has a small volume, I will be able to find a cycle of large weight. And once I find a cycle, I'll reverse on that. I'll find such a cycle and reverse, basically change on it, and that will increase my volume as well. And I'll keep doing this as long as my volume is small. That's basically the whole algorithm. So I'll just briefly tell you a couple of lemmas about it. First is the determinant to cycle lemma, which says that if T denotes, let's say T denotes the set of vectors in the optimal solution, if the volume of T divided by volume of S, which is your current solution, is way, way bigger, that means you are really far away, right? That there is a way better solution. Then there must exist a cycle in this graph such that the product of the weight of the cycles is basically the size of the cycle to in exponent another, like a 5 times the cycle. This proof is not actually very difficult. This is a very slick argument, but in interest of time, let me just, basically the point is how do I have to relate the volumes to the weights on these edges, right? The volume of the optimal solution and volume of my current solution, this ratio to the weights on the cycle. And the way to do it is actually, yeah, maybe let me just do it in 1 minute for you, is you say, let me look at the optimal solution. Let me write down all these vectors in the basis of S. If you do that, you will basically, this is exactly this linear equation. Vt will be equal to Vs times A, where it will be a D by D matrix. It will be indexed by T on one side and S on the other side. And the entries of this A are exactly the weights on these edges, right? Okay, good. And I'm telling, and what is right? Our weight on the volume of T by volume of S is exactly determinant of Vt by determinant of Vs, right? We know the volume of T is exactly the determinant, right? And because these are D by D matrix, this determinant ratio is exactly determinant of A. So determinant of A, when you tell me this ratio is large, you're telling me determinant of A is large. Pardon? Up to sign, yeah, sorry, yeah, exactly. I should have put an absolute value over here. Yes, thank you. Yes, I should have put absolute values over here. Determinant is at least D to the D. And now you say, okay, if the determinant is large, there must be a permutation which will evaluate product of these absolute values of these AUVs of the weights will evaluate to be large, right? And which will be up to D factorial. D factorial, I can eat up, have D to the D over there. And each of these permutation, this permutation will correspond to a bunch of these red edges. And I'll select the blue edges appropriately. So this will get a collection of cycles such that the product of these cycles is large. So one of these cycles must be large. Right? This is the kind of the only argument I'll do for you. And I'll just, so after doing this, there'll be only 3 things to do. Firstly, at this I showed you there exists a cycle, right? The optimal solution tells me if the optimal solution is large, there exists a cycle. So the first thing is how do you find this large weight cycle? This again, you can reduce to finding a negative length cycle in an appropriately weighted graph. Okay, so I will not do that. Second thing is, if I find this cycle, how does the weight of the cycle imply a change in the determinant, right? So if I change the weight, I change the cycle, right? I say I find this cycle, all these vectors I'll replace by on the other side of the cycle. Now I've got a new set. How's the volume of this new set, right? How they should depend on the weight of the cycle somehow. Okay, that's something, and that's basically what we show is that the last cycle implies last determinant. Okay. In the interest of time, maybe this is where I should really stop for you. The argument are not very difficult. The last part is very technical, but it requires some more care. So let me not go over there. So let me just skip to the final result. Is basically there is this joint work with Brown, Lada, who are PhD students, and Pittu, who did an internship over here a couple of summers ago, I believe, with Arindam, who's a grad student at CMU now. Basically, you can get a solution S, which is about 1 over D to the D times determinant. And again, as we are interested in dth root of the determinant, this will imply a D approximation, right? Or a D approximation. Okay, so let me just conclude. So I introduced you the determinant maximization problem, and I told you some both combinatorial and convex optimization methods are applicable to this problem. In terms of the combinatorial methods are certainly more used in practice, especially for cardinality constraints, and now they have some provable guarantees as well. A big open problem for all of these is that, especially for MATROID constraints, many of them we don't have any constant factor approximations, and that's something we believe is the right answer. Actually, I feel the right answer is something like either E or 2. We don't have any bad examples worse than those. In some sense, that really should be the right way. The other thing, which is I would say a big area of research which has not been done so much, is where we focus on just the determinant objective, which already has many applications. If I change to other spectral objectives, like the minimize the trace of the inverse or maximize the minimum eigenvalue, each of the under some combinatorial constraints, these are again have many applications. Actually, many other combinatorial problems have been studied, which will form a special cases of these problems, like we did for determinant maximization. Somewhat cardinality constraints are much better understood. Actually, I would say cardinality constraints, we have a very clean understanding. I haven't written a lot of giving you references, but we do have a much better understanding. For more general combinatorial constraints, unfortunately, we don't have. Actually, there's a beautiful work on Cadison's Singer problem, which you can actually say that this is really a special case of the minimum eigenvalue problem for this, even which is a major breakthrough result, and those results are completely also non-algorithmic. But from an approximation point of view, we really don't have much of understanding of those. Okay, I think I'll just end over there. Thank you. Questions, comments? Yes.
The weights will change if one of the vectors is replaced.
Yes.
But then you're saying the entire
yes, replace exactly. So exactly, that's really the challenge, because the way I put in the weights is exactly very good. Like this is exactly the point I wanted to get across, which I didn't in the slides over here. What I've got, like the weights I put in is exactly if I just change one vector, right? But really when I change a bunch of vectors at the same time, how does the volume change? Actually good. So let's say I change, like this is my cycle I got, right? This is a L by L cycle. Okay, this is the cycle I get. So where my weights are only on the red edges, right? So those are, I'm finding the cycle as if I'm just like replacing one vector, but I've not changed all of them. How much will my volume change? Volume will actually change exactly proportional to the determinant of this matrix. What is this matrix? You put all these vectors on one side and all these vectors on the other side of your matrix. So you form an L by L matrix. And the entry you put is look at the L, all the red edges, right? That's a complete bipartite graph. If the weight is 0, you just put a 0 and you put those entries over here. Okay? So you can show basically the determinant of that matrix will exactly govern how the volume will change. Okay? Now the whole point is all these red edges of the cycle will, if you place this appropriately, the red edges form the diagonal entries of this matrix. So what you're telling me is the product of the diagonal entries is large, but we need to show that the determinant of this matrix is large. So somehow the off-diagonal entries need to be small. And the question is, why will the off-diagonal entries will be small? This is where we use that it's the shortest hop cycle. Every off-diagonal entry corresponds to another red edge, which I'm not showing in this case. If I plug that edge in, I know it's not such a heavyweight cycle. It's not like I found the shortest hop cycle, which was a large. Because it is not, that would imply that this entry must be small. Okay, so you use that property to show all the off-diagonal entries are small, and then you can show that the weight of the determinant of this matrix is closely related to the product of the diagonal. That's the only term that dominates among all the d factorial permutations. So exactly that's the point of what I wanted to get across. Yes. Yeah.
And a follow-up. So if so you did this exchange of and then you when does the process stop?
So you keep doing it, because what does the theorem say is that if the volume to T over S is more than this, then I can find a cycle. So when you don't find such a cycle, that's when it stops. So then I'm sure that the optimal solution is not very far away. How many iterations? Yeah, so every time you increase your volume by at least a constant amount, so it won't take too much. So you can show basically a large constant. The number of iterations will not be too large. Correct, exactly. So when you stop, basically, yeah, then you know the optimal solution can't be too large, otherwise you would have had the cycle to come. The other, actually, other exercise for the students in the audience is actually how do you find this large weight cycle? So how do I find a cycle whose weight is size of the cycle times 5 to the c? Such a thing is a nice simple exercise. Actually, it's a nice problem in a grad algorithms course as well. Yes. So there is another comment or question. Yes. Okay, good. So yes, so you should think of, for example, I told you this work on Nash social welfare. So yeah, exactly. So this I said is a special case of the problem, Nash social welfare. And what is the, how do you formulate it as a special case? Intuitively, you pick, right, given this allocation problem, you somehow put a vector, your vectors are the following form, they only have one non-zero coordinate. All the other coordinates are so there actually, yes, all, if you have that thing, all of these, like you can get a 1.45 approximation and so on, which sit over here and the students have worked extensively on and so on. So, but there things become, the problems are, you can apply more algorithms which use that property a lot more. They look at like kind of, rather than thinking of it as a determinant problem, they view it as some kind of a market design problem. Okay, a very different interpretation that allows them to get the better algorithms for that. Nonsense. The other special case, as I said, was these network design problems. Here also, from some very special cases, we do know better algorithms as well, where you can interpret some of these bounds in a more combinatorial way, because you're like you have a graph and so on. So you can sometimes interpret some of these quantities more combinatorially, and again, you can use those combinatorial bounds to get better approximations. So in some sense, yes, whenever it's special, you really want to interpret it somewhat differently than just a determinant to get more structure. So like in the over there, you could interpret it some kind of market design. Here you somehow interpret it in some kind of basically as a graph theoretic measure, which you can
Do we have any other questions? Yes, the speaker. Small appreciation.
Okay, thank you.
So we can now move for lunch.